We want to talk a little bit about alternative non-chemical strategies that we see around the United States. One of the things that we want to look at are some of the things that we're seeing around the United States a lot is pulsed electrical fields, which are normally your Dolphins, your pulse pure type Griswold systems. We're still seeing magnets or electromagnetic fields trying to be used to control water treatment programs. And up here we're seeing, in some parts of the country, we're seeing ultra soft water as an alternate strategy for water treatment programs. So I want to try to focus on the three of these things, but also give you some ideas of how to handle the people that knock on your door and say, hey, we got the greatest thing since sliced bread, can we talk to you about not using chemicals? When you think about why would you want to consider something like this? Well, certainly it eliminates the use of hazardous chemicals on your site. It's a good thing. Eliminates drum handling, shipping. It's better for the environments that you're not dealing with hazardous products. There's normally less manpower involvement. There's perceived and or actual better technical results depending on how good your water treatment program is. And there are actually some lead points that you can achieve by using alternate strategies like that. So it's a good thing, and I honestly believe sometime down the road something is going to be developed to help reduce the amount of chemicals being used for water treatment programs. We still want our biological counts in control. We still don't want to have scale formation in our systems. We certainly want to make sure that the fouling and filtration are still a part of the program, and we certainly want to make sure our corrosion rates are there. You can achieve these now. Okay, so let's talk a little about the electrical pulse devices. In particular, these are the pulse pures, the Dolphins, Griswolds that we see out there. Their scale control methodology, they claim, is basically selectively precipitating calcium carbonate in their evaporator section. So they have an area right there where they put an electromagnetic pulse in there, and they actually try to precipitate calcium carbonate out of solution. And these are, once they're precipitated, it really doesn't adhere to any heat transfer surface. It's just a particle. So it eventually migrates to the tower basin, precipitates out, and you can remove it through filtration or blowdown. Corrosion control is done through LSI. Okay, so remember we talked about they raise the water quality up in a scaling state. So we really don't have a corrosion problem, but they try to precipitate some of that scale for scale control. So we understand the corrosion principles behind some of that stuff. And then their biological control, they claim, is they do it by damaging the cell walls, by the pulse fields, or they actually try to trap the bacteria in the water into their seed crystals that they develop in there. So they try to precipitate it basically out of the water for biological control. Okay, so what do we actually see? When we go to a client accounts, they say, hey, Homar, let's check this thing out. Let's do the analyticals. Let's find out what's going on. We actually do see fairly good scale control. I mean, we're running some accounts right now, and I know the water quality is a little softer here in some places, about 6 cycles of concentration, and we don't see scale. So that's a positive thing. So we see some effects there. We don't see good corrosion control. Now, there's 2 types of corrosion. There's general corrosion, and there's also biologically influenced corrosion. Okay, the general corrosion, we see pretty good results. Like on the copper coupons, we see fairly good results on copper corrosion, but obviously we don't see very good mild steel corrosion. And it's because of biological problems that you can see. That's one of the slides you've seen earlier where we have bacteria basically growing on the program. We do see good bulk water bacteria control. So in other words, when you do those dip slides, we see good clean dip slides. We see pretty good results on that part. But what we see is very poor surface biological. So these bacteria seem to be migrating to the surfaces, setting up shop, setting up home, and they actually grow. So here's an example of a coupon that was pulled. It's all brown and slimed up and everything else. So it's very obvious that the bacteria is growing on the pipe surfaces. That's what also causes the corrosion on that. When we've actually taken a look at some of the equipment after it's been inspected, we see this is basically a header box of the condenser. We pulled the end bells off. So you can see the head box right there. By the way, this is a gray epoxy-coated tube sheet. If you notice the color, it's not gray. This is all the biological fouling that we've seen in the tube sheets. If you look at some of the borescope pictures on the tube sheets, we actually see biological growth growing on the tube surfaces themselves, which obviously causes pitting underneath those tubes and is going to cause some damage. If you exceed the limitations of their units, you can still see scale formation, just like you can with chemistry. So we've seen some towers, so we've seen some pretty high scale formation. The problem with some of these units is that it's a piece of equipment, so the light blinks on the wall. Everybody says the light's blinking, everything's working. Yeah, light's blinking. But unless you're doing some chemistry to make sure things are working, you don't know if the light's just blinking or if it's actually doing something. So Some of the things is you still need to run the test. You still need to do your maintenance behind some of these programs on that. So we basically see that they do a good job with scale, a fairly good job with general corrosion, a good job, as far as limiting the chemistry, but we don't see good biological and good corrosion rates with these type of systems. And we'll get to the reason how we fix that. So how do we go about fixing that a little bit later? If you're looking at some of the systems, especially we see in California, we also see this in high hardness areas around the country. They actually put softeners on the system, and the purpose is to remove the calcium out of the water, which is fine. That's how you control scale. So we understand the scale control mechanism through using water softeners is to remove the calcium magnesium out of the water. The corrosion control is fairly simple. We drive the cycles up. Again, we make the water kind of scale forming, but without the calcium. So the high alkalinity in the water and the high minerals prevent the systems from corroding. So that's pretty good. And in most cases, a lot of times they still need to feed some form of biocide around the cooling towers just to control the biological. There are some people that claim that if it's above 9, it kind of inhibits the bacteria growth on that. And in some cases, we do see some of that in the bulk water, but again, we don't see it on the surface where there's still questions about that. Please remember, if you're looking at softeners for zero discharge, it's not really zero discharge because you do have to regenerate the softeners. So when you regenerate the softener, you have to go through a water process that introduces a brine solution to regenerate them, and that is a waste stream on there. So there's not really total zero discharge with regard to water savings. So basically what we do with soft water applications is we see good scale control. We obviously see good corrosion control. That's two good things on that. The jury's still a little bit out on the bulk water and the surface biological control. And then, of course, the anaerobic bacteria, we don't see that. Remember about the bacteria. Bacteria finds a way to survive, okay? If you kill them, they'll develop another strain, okay? I mean, they're going to find a way to survive in the environment. So you're always going to have to deal with some form of biological activity. There is one negative consequence with using water softeners and ramping up those cycles. And that is, what happens if the softeners fail? Okay, or you lose control of the softeners, or something happens to the softeners. You got to remember, you've got a water quality that has been void of calcium because you've been softening the water, so it's got all the alkalinity sitting there waiting, loads of it, because you're cycling it out. So if those softeners fails and all of a sudden you introduce a fair amount of calcium into the water, that water is ready for that calcium. And immediately what's going to happen is you're going to start scaling the cooling towers. I mean, within a couple days. This is a situation here in Indiana where the plant was using soft water, getting the cycles up, and they lost the softeners for a month. No one was testing. No one did anything. They just felt everything was working until they saw their towers, and, of course, it all scaled up fairly quick. So you need to be careful with some of this stuff. And it does require a little bit more maintenance. It does require a little bit more effort as far as testing and balancing because you're trying to push the limitations of the chemistry in the water. When you look at ozone, ozone made a run about 10 years ago where they said, okay, we can just put ozone in the water and it'll solve all your problems. It actually did fairly well, to be honest with you. If you look at ozone by itself, it's basically oxygen on steroids. They take oxygen, they through a arc process, they bring it up to O3 state. It's a nicely smelling molecule. If you're in a lightning storm and you smell that sweet smell, that's basically ozone right there. It doesn't want to be there. It wants to go back to O2. Okay, so in that process, it's a very good biocide. It's probably one of the best biocides that I've ever seen in its ability to control biological activity. The pain on ozone is developing it. It's to producing it and having enough to get it in there. It's very energy intensive process to take O2 and bring it up to O3 and then be able to pump in the water at a high enough concentration to actually kill. So because ozone did a very good job with biological, we saw very good biological control. And because there wasn't a lot of biological, we didn't see a lot of fouling because of that. And then, of course, they tried to ramp up the cycles again for corrosion control. We all know about that. The only problem is it had nothing to do with scale, and every tower scaled, basically, because of it. So because of that, it's just not as – it failed over here, and therefore it only picked 3 of the 4 quadrants that it actually worked on. So if you're using ozone, you do have to be careful because how are you going to control the scale over here on this side? If you were to feed a phosphonate, that we talked about earlier for scale control, the problem is ozone chews that up too. So anything in its path, it basically goes after. So that we don't see ozone anymore very much as a standalone program, but we see it used as a sporadic case and maybe not at all because of the cost it takes to do it. Okay, so how do you evaluate? I mean, the concept's good. Okay, if we could develop something, if I could develop something that could work, then I'm going to retire very quickly on this. So we still want to use the performance standards on that, and maybe it's a combination. Maybe if it does 3 of the items, maybe we need to supplement it with something and create that kind of program for people that have that process. We do have clients that are using some of these alternative strategies because they can't discharge water. They can't discharge for environmental reasons. So they have to be forced into some of these alternatives. So we try to look for some supplements to help them control the biological activity while the units are doing a good job with scale and corrosion. So there are some sequences that you can use to help reduce the amount of chemicals, or if you're under pressure environmentally, to help you eliminate the chemical usage. First thing is, when you want to evaluate anything, make sure you understand what the performance standards are, have them outlined, agreed upon with the supplier of the alternate strategy, and then make sure you have the ability to monitor the process. Don't install it and wait to see your inspection and go, well, what happened? Okay, or wait till something happens. Start your monitoring process right away. And we have the monitoring ability. We have corrosion coupon racks, so you can monitor corrosion rates. We have the biological dip slides in the field. You also have lab backup capabilities. You can go to any lab and have the things analyzed for mass balances and everything else. So you have the ability to be able to monitor these programs, and we normally give them about a 90-day window to prove to us in phase 1 that they are addressing scale, corrosion, biological activity. Okay, if they meet those requirements, then we go to phase 2. Let's keep it going, with the intent that if it does do well, then obviously customers probably going to maintain that form of alternate strategy, and obviously they're going to be able to write a nice paper, and they're going to have all the data behind them, and so it helps them develop their strategy around the other cooling systems. The other thing that I love asking these people is, show me the data. Okay, show me the data. Okay, you've got a strategy here. You think this is what's going to work. Okay, show me where you've done due diligence on mass balances, on biological activities, on anaerobes, on surface bacteria. Show me the data. Well, don't worry about it. The guy down the road uses it. He claims by it, swears by it. I said, that's okay. Show me the data on that. So if you start asking for data and stuff on that, then we'll find out where their strategy is. When water treatment companies develop a new product, okay, that they think is their next generation, they run it through a very rigorous process. They do their lab work. Most of them have what they call pilot cooling towers, where they have small little cooling towers in the labs where they actually simulate cooling towers, grab all that data. They normally have a client that have it's the cooling towers that they can put at risk. So they go out in the field, and at their cost, they grab all the data. So they basically do an awful lot of research to make sure this works around the country. A lot of these companies don't do necessarily that. They just put it on there. If it works, fine, they go on to the next one. So show me the data, and you might find yourself where you are with that client. The second thing is, be prepared to supplement the program with biocides. The number one driving force, with the exception of ozone, is basically biological activity. So if you might want to be able to supplement with biocides and still be able to achieve your corrosion and scaling rates with these alternative devices, just you might have to supplement with some biocides and be able to control that. So don't necessarily shut them out, I mean, if it doesn't work, but you might have to supplement that a little bit, and it still might be a great venture that you might want to do with your cooling systems. And again, you guys have the luxury up here is that you have a colder environment up here than south, obviously. Your water quality is a little better. It's actually a lot better in a lot of places around the country. So there are some rooms where some of that technology might be able to come in with some supplemental biocides and actually do a fairly good job on that. And the last thing is, you probably are still going to need some form of filtration. We would recommend this on all cooling towers anyway. This actually helps reduce the risk because it does help remove helps remove suspended solids. So it's a good idea to have some form of filtration on there. And again, our preference is the sand filtration or high efficiency sand filtration on there.